Hey, welcome back to the channel. This is Jones speaking, and today we're going to go over how to do a whole bunch of different machine learning algorithms in just one line of code. And for that I mean one line for each algorithm. Again, this is Jones speaking. So here we go. I just wanted to start out and give you all the information up front. You don't have to wait till the end for it. These are each of our lines. If we want to do logistic regression, we're going to write this line. Obviously put your data here and your labels here. If we're going to do k-means clustering, do this line, etc., 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 etc. So let's go into a little bit about each one of these, and if you'd like to stick around and see how they perform, how they run, let's dive into our data set real quick. We are looking at the Titanic data set, which this is a record of almost all of the passengers and a bunch of information about them, and our goal is to predict whether or not a given passenger would have survived the tragedy on the Titanic using machine learning. Obviously, if you're keeping track of this, if you're paying attention, you'll know that these are not going to perform well. Or I guess there's no way that we're going to be able to get 100%. There's some real world knowledge that goes into interpreting this data, and here is what the data actually ends up plotting as, right? So we're looking at everything above this little line is female, everything below is male. It's grouped by, looks like age and age here, and then how much they paid for their ticket. So we have really spread out data. It's going to be a little bit difficult to actually tell just off the bat how we're going to do. So let's dive in with logistic regression. Let's talk about our data real quick so you can understand what's going on right in the beginning. First off, I've said this before and I'll say it again. Every machine learning algorithm does better when you're able to convert all of the data into numbers. And I say this as somebody who does NLP professionally. We gotta turn all of our language data into numbers, otherwise it doesn't work. So looking at our data, we see this name column is gonna have to go, this sex column, because, and this is just, it's binary sex. You know, they're not asking on the Titanic whether someone was non-binary. That would have been very weird back at the time, but for our purposes, this is just a binary here. That needs to be converted into either a 1 or a 0. This age has some missing portions. We're going to need to fill this. An easy way to just fill it all up is to fill with the median or the mean. I'm going to pick the median because it's the middle age. We see the ticket is a combination of letters and numbers. Some of them are letters, some of them are numbers. Some of them have special characters, like this one. So I'm just going to throw ticket out. The fare is all numerical, so we'll see if there's a statistical correlation there. The cabin is too sparse and too much of a letter number game to keep, so we're going to throw that out along with the ticket and the name. And then embarked, we have C's, we have S's, and we have Q's. And it looks like there are a couple that are missing. So we can fill those couple with whatever the most common one is, and then just turn C's, S's, and Q's into 1s, 2s, and 3s for our purposes. I would not recommend, like, I'm blazing through this and I'm not really paying attention to a lot of the portions of the data that would actually help you professionally. So I have to give you this disclaimer that working with your data to make sure you understand exactly what's going on in here and what's going to be statistically significant for the model that you choose is going to be the longest, the most arduous, and the hardest part. And it's, like I said, it's going to take a while. So don't blaze through it like me. But let's get to actually using logistic regression. So you'll see here with our data frame, we're doing exactly what I said. We are taking the name, the ticket, and the cabin, and we're dropping them. We're filling the age with the median. We're filling embarked with pad. and then we're turning male to 0 and female to 1. In that sex column, we're turning C to 0, Q to 1, and S to 2 in that embarked column. And then we're doing the exact same thing to our test data set, which you'll notice the only difference here is it doesn't have the survived column. These are all passengers that are not included in our training set so that we can get a really good test and really get a good idea of how well these algorithms perform. So let's go ahead and run this one. Here we go. We have our confusion matrix and our accuracy score on our training and our test data. Looks like we got 80% training, 76% test. And this is likely going to be the best one of these algorithms, and I'll tell you why. When you look at this, if we were to throw survived in here, see how it squishes it all down into either a 1 or a 0, and it's still bucketed male and female, it's still bucketed by age, but when we squish it down, you can see there's a very clear decision boundary here. And that's what this logistic regression is trying to draw here without squishing it at all. So we can get a lot of this correct. You're seeing 76% on there, right? And that is awesome. That's really good. The rest of these, I'm not saying they're worse. Actually, some of them I consider a lot better, but because this data set is just so all over the place, and understand that there's some real world knowledge that goes into interpreting the data set. You have, if you were a woman and if you were a child, you are actually a lot more likely to survive on the Titanic, partially because, you know, the norm at the time was to get women and children to safety first. And so a lot of the lifeboats were filled up with that, and that it doesn't really matter, but that's just telling you that there's some real world knowledge that's going to defy statistics when we are just taking it at face value with an algorithm. So the next one, k-means clustering. This, as opposed to logistic regression, isn't used for classification. This is used on unlabeled data. So you'll see down at the bottom it's a little bit different. You know, we are, instead of going for an accuracy here, we are grabbing clusters. And let me show you what those end up looking like with our data. We've picked, you can see here, we've picked 5 for our number of clusters to grab. On here you can see our 5 clusters that I've identified within the data. This is really useful for things where you don't have labels. You just have a bunch of data and you're trying to determine labels for your data. There's no really accepted way of determining how many clusters you should be drawing. I just picked 5 because it seemed like a good bucket for this. In real life, you would want to use some information theory and run this multiple times to determine the optimal number of k-means clusters that you actually want. And then what you'll do is use the next algorithm, the k-nearest neighbors, on those clusters to figure out where, well, you'll use k-nearest neighbors as your classifier and use the clusters as your labels to figure out where other things belong. And we can see that here when we throw this through. K-nearest neighbors is the first one of ours to actually get 100% on our training set. It only gets a little bit less than 2/3 on the testing data, meaning it's having trouble drawing. But basically the way that this works is it's taking the average of however many clusters or however many neighbors are near it and picking a classification based on that. So we have 1 here to make sure that it's going to be a binary. If we had 2, it would measure the distance between the 2 and take the average of that distance, and that would be the class. The reason we can't do that is because we're trying to estimate either a 1 or a 0. So k-nearest neighbors really does not perform well, and you can see that here. It's, you know, only 13% better than random, like absolute 50% random. It doesn't do well in binary classification, but it does very well if you have a lot of data and a lot of labels. So if we were going off of all 5 of our k-means clusters, this might perform a little bit better if we were able to do 5 neighbors for it. But all in all, this is a strong combo for getting a read on data that you don't have labels for. The next one we're going to go into is a support vector machine. This is similar to a logistic regression, where a logistic regression is attempting to draw one line through this data. A support vector machine is attempting to draw a line between the closest data point on the female side, right here probably, somewhere in here, and the closest male data point. So this is probably the closest female, this is the closest male. It's trying to draw straight lines between those as a decision boundary, and then to support that vector, that's why it's called a support vector machine, you're trying to space that out as far as mathematically possible. Give yourself a nice large decision boundary. Let's see how well it will perform on our Titanic data set. Looks like it's not too well. Again, because this data set is so all over the place and so mixed, there's no way that this would perform well. This would be a lot better. Like you could, I don't recommend doing this, like deciding your life this way, but if you were in college and weren't sure what to major in, you could rank your skills and rank your classmates' skills and label them based on their majors. You know, you could rank your skill at math, your skill at art, your skill at language, whatever you'd like. And this will attempt to draw a decision boundary between all the different classes that you put, and then you can enter in your own self-ranking, and that would help you figure out how to, or like what to major in. I recommend doing that just as like a fun project. Don't base your life off of machine learning, otherwise you'll run into lots of problems, especially as an amateur. The next one we want to do is a decision tree, and this is the first one that is really helpful for humans. As opposed to these ones, these can be confusing when you actually look at them plotted out on a graph, but a decision tree is human readable. I'm sure we've all seen examples of a decision tree before. Where, yeah, here's this. Here's a decision tree. It's just yes, no binary, trying to get to whatever class is at the bottom, right? So this is very helpful. I've used decision trees to explain other models, even if the decision tree is getting lower accuracy, which let's see how well it does here. It's our second one to get 100% accuracy on the training set. That was a little bit expected because it's literally creating decisions based on each of the columns in our data set, each one of these. And it's splitting them based on that, so we were hoping it would get 100%, and it did, and we've got 75% accuracy on our real test data. This is, I guess support vector machines are the first one, but support vector machines are the first of these three where running it multiple times, see if we do this again, we're getting a different accuracy on our test data than we did before, because it is splitting statistically instead of splitting the same way every single time. This is helpful. This is the basis for what's called a random forest, where you take a bunch of different decision trees, let them just be as random as they want to be, run it like 100 times all in parallel, and then pick whichever one performed the best on the testing data. And the way that you would do that is instead of importing this decision tree classifier, you'd import a random forest, and then you'd give it a number of iterations. So decision trees I've used to help explain other models, especially to people who are not statisticians, who are not mathematicians, who don't need to know all of the minutia about what's going into the model. They just need a visual for explaining why it's making some of the decisions that it's making. That can be really helpful. This last one is one that is very fascinating. A lot of people use nowadays. I work with these daily. Not necessarily these are multi-layer perceptrons, and this is a regressor one, not a classification one. But I work with neural networks daily in my day job, and they are really cool. They're based off of the idea of how a human brain works. Let's look at an image. Here's one. They're based on the idea of how a human brain works, how we have synapses that connect to each other and light up when certain things happen. So we have our input, which is just going to be our actual data frame, the actual test. And then, oh shoot, where is it? There it is. Each of those will go to a number of features that is defined, and these will either become a number that's not 0 or stays 0. And that if it becomes a number that's not 0, it's turning on in quotation marks, and if it stays at 0, it's turning off. And those are all added together and will give us our final class, which this is exactly what we're doing. We have either a 0 or a 1 as our final output. And we are doing a pseudo sigmoid here. I decided this would be, it's not easier than importing an actual than doing an actual sigmoid. I just thought that this would be a little bit simpler, and I'm not throwing too much vocabulary at you. Again, here's our actual one-liner for our neural network, and then what that sigmoid is it essentially squishes all of the values that come out of the neural network to either a 1 or a 0, somewhere between them. And we're saying that if it's greater than 0.5, greater than that halfway mark to 1, then just make it a 1, and if it's lower than that, then just make it a 0. So let's see how well this does. Looks like we're getting 80% accuracy on our training set and 71% accuracy on our test set, and that's pretty dang good, especially for a first run. A lot of the work that I actually do for my job revolves around making this better and making it perform better. I figure you guys don't necessarily need that, especially if you're just a hobbyist. But if you'd like to learn it, that's the next step, because you have your one-liners, you have your program, you have your network, which all of this is thanks to Sci-Kit Learn. This is Sci-Kit Learn. They do a lot to make sure that every single one of these looks really similar. They follow the same API. They have that fit mechanic. They have that predict, I guess not mechanic, but method. The fit method, the predict method on each one of these makes it really easy to interchange and experiment to find the best one for your use case. And you can use these for pretty much whatever you'd like. It is really helpful to mess around with these in your spare time. The more time you have with these, the better you'll get to know them. And for anyone who would like the code, I've open sourced it on my GitHub. The link is in the description. Thank you so much for watching, and I'll get out of your hair.